Welcome to The Explainer. Today, we're going to dive right into the fascinating, completely invisible relationship between electricity and magnetism. We flip switches and power up gadgets all day long, but we rarely stop to think about the invisible forces practically dancing behind our walls. Well, that changes today. So let's kick things off with a bit of a provocative question. What do a simple compass and a lightning-fast electric current actually have in common? At first glance, they seem completely unrelated, right? One helps you find your way in the woods, while the other charges your phone. But as we're about to uncover, they are quite literally two sides of the exact same coin. To really wrap our heads around this, we have to jump back to 1820 and look at a guy named Hans Christian Ørsted. Now, Ørsted accidentally discovered that a compass needle got deflected whenever an electric current passed through a nearby wire. This total accident proved that these two distinct phenomena were actually part of the exact same scientific puzzle. And honestly, his realization laid the groundwork for modern tech we literally can't live without today, things like radio, television, and fiber optics. Here is the quick roadmap for today's explainer. We'll cover how electricity meets magnetism, mapping the magnetic field, the right-hand thumb rule, loops and solenoids, the left-hand force, and then wrap it all up with your home electric circuit. Let's get right into it. Starting with Section 1, Electricity meets magnetism, the invisible link. Now, before we get into the complex currents, let's just quickly lay down the absolute basics for how magnets fundamentally behave. A compass needle is actually just a tiny bar magnet. It's got a north-seeking pole pointing roughly north and a south-seeking pole pointing south. And the universal rule of magnets applies here. Like poles will always repel each other, while unlike poles, or opposites, will constantly attract each other. Keep this basic push and pull in mind because it is the engine driving literally everything we're about to discuss. Moving on to Section 2, Mapping the magnetic field, seeing the unseen. So, knowing that magnets push and pull is great and all, but how do we actually visualize a force that's completely invisible to the human eye? Well, by sprinkling tiny iron filings on a cardboard surface around a straight copper wire carrying a current, we can basically watch the physics happen in real time. If you give that board a gentle tap, those tiny metal detectives naturally align themselves to reveal the hidden blueprint of the magnetic field. They actually form these perfect concentric circles wrapping right around the wire. The absolutely crucial takeaway here is twofold. First, notice how those circles get larger and larger as you move away from the wire. That tells us that the magnetic field strength decreases as distance increases. Second, if you were to crank up the electric current flowing through that wire, a compass placed nearby would deflect way more sharply. Simply put, more current equals a stronger magnetic field. Which brings us to Section 3, the right-hand thumb rule, grasping the direction. Okay, so we know the field circles the wire, but which way is it actually spinning? Clockwise? Counterclockwise? Let's figure it out. I actually want you to physically follow along with me right now. Hold your right hand out. Imagine you're grabbing that wire. Now point your thumb in the exact direction the electric current is flowing. Okay, curl your fingers around that imaginary wire. The direction your fingers wrap is the exact direction the magnetic field lines are circling. It's like this beautifully simple built-in cheat code for physics.
Next up, Section 4, Loops and Solenoids, Building Power.
We've got the basics of a single straight wire down. But what if we start bending it to stack and amplify all that invisible power? Let's compare two setups. If you bend the wire into a single circular loop, the concentric circles of the magnetic field grow larger as they move toward the center, eventually stretching into straight lines right in the middle. But if you take that same wire and wrap it into a tight cylinder with many turns, something we call a solenoid, well, something amazing happens. All those individual loops add up. The field inside the solenoid forms strong, parallel, straight lines. It becomes a totally uniform field, acting exactly like a standard bar magnet, complete with a clear north and south pole. And honestly, this is one of the coolest applications in all of science. Because that solenoid's internal field is so incredibly strong and uniform, if you place a piece of magnetic material, like just a standard soft iron rod inside it, the iron instantly becomes magnetized. You've just built an electromagnet. And the absolute best part, the moment you switch off the electric current, the magnetism vanishes. It's a powerful magnet that is totally controllable. All right, Section 5, the left-hand force when fields collide. We've just seen how electricity creates a magnetic field. But what if we take a wire that's already carrying a current and literally drop it into a completely separate pre-existing magnetic field? Well, French scientist André-Marie Ampère realized that this relationship has to be a two-way street. He proposed that if the current exerts a force on a magnet, the magnet must exert an equal and opposite force back onto the wire. When these two magnetic fields collide, they don't just pass through each other quietly. The magnet actually pushes back on the wire, causing real, physical, observable movement. Get your hands ready again, but this time use your left hand. We can actually predict exactly which way that wire will be physically pushed using Fleming's left-hand rule. Stretch your left thumb, forefinger, and middle finger out so they are all at right angles to each other, like a 3D axis. Your forefinger represents the magnetic field, your middle finger points in the direction of the current. If you align those two, your thumb is going to point exactly in the direction of the force, meaning the physical motion of the wire. Now, here's a detail you absolutely don't want to miss. Experiments show that this physical push on the wire is at its absolute strongest when the current is flowing at exactly a 90-degree right angle to the magnetic field. Maximizing this force is the whole foundational technology behind building things that actually move. Electric motors, loudspeakers, complex measuring instruments. They literally all rely on deliberately colliding these fields at right angles to generate real physical motion. Finally, let's hit section 6, your home electric circuit, bringing it all together. Okay, let's pull all this abstract lab physics into the real world and see how it actually powers your house every single day. If you strip back the walls of your home, you'll find that domestic circuits generally rely on three distinct wires. You've got the live wire, usually wrapped in red insulation, which acts as the positive path, bringing the 220-volt power in. Then the neutral wire, typically black, which is the negative return path completing the circuit. And finally, the earth wire, insulated in green, which runs all the way down to a solid metal plate buried deep underground near your home. Now, your house actually takes these incoming wires and smartly splits them up based on your power needs. You have your heavy-duty 15-amp circuits designed specifically for power-hungry appliances. Think water geysers or air coolers. Then you've got separate, lighter 5-amp circuits for things that demand much less current, like your standard light bulbs and ceiling fans. But let's talk about that green earth wire for a second, because it is literally a lifesaver. Imagine the live wire inside your metal toasters somehow gets frayed and touches the metal casing. Without an earth wire, the second you touch that toaster, you become the circuit. But because that metallic body is connected to the earth wire, it provides a super low resistance path straight into the ground. It ensures that the leaked current flows safely into the earth, preventing you from getting a severe electric shock. It's an automatic safety net built right into the grid. And that essentially brings us to the end of today's explainer. But before we sign off, I want you to just look around your room right now. Check out your fan, your speakers, your phone charger. Where are the unseen magnetic fields and electric currents silently pushing and pulling to make your modern life possible? This incredible physics magic is happening everywhere, completely invisibly, right in front of us. Keep questioning, keep learning, and I'll catch you on the next explainer.